This is Algebra 2 Pre-Calc, and we're doing 10.8 in Pre-Calc, which is polar graphing. So in example 2, we're going to test r equals -1 plus 3 cosine theta for all three types of symmetry, and then we're going to graph it. So let's start. Again, you don't have to memorize the test for symmetry, right? We're going to slide over here. If you were asked to do this in like a homework or something, you could look up the tests on page 757. And that's fine, right? This is not the kind of thing, it's a useful skill, but it's not something that's worth memorizing per se. So I'm going to start by testing for theta equals pi over 2, right? So to do that, the point I want to use is -r comma negative theta, right? So if I plug that in here and I get the exact equation back when I simplified, then I know that I have something symmetric about the line theta equals pi over 2. So -r equals -1 plus 3 cosine of negative theta. Well, we've already seen that since cosine itself is an even function, when I plug a negative in, nothing happens, and I just get 3 cosine theta. So I get r equals 1 minus 3 cosine theta, which is definitely not the same as the original function. Like, it should look exactly the same, and it doesn't. Cool. If I test for theta equals 0, or the polar axis, right, then I'm going to plug in the point r comma negative theta. So I'm going to get r equals -1 plus 3 cosine of negative theta. Well, we already saw that 3 cosine of negative theta doesn't change anything. It just is still a 3 cosine of theta. So I get -1 plus 3 cosine theta, and that's a yes. So I do have symmetry about the polar axis the same way that I did in example 1. If I test for symmetry about the pole, right, the point I want to use symmetry for the pole is I want to use -r comma theta, right? So I get -r equals -1 plus 3 cosine theta, which is the same thing that happened here. So if I simplify, I'm going to get the same no. So again, I only have a graph that is symmetric around the polar axis. Now let's look and see what happens when we graph that in our calculator. So I'm going to put in my -1 plus 3 cosine theta, right? So there's my R1, right? And I'm just going to go ahead and zoom 6 because I'm kind of lazy. So we'll zoom 6, right? And I end up with a graph that is symmetric. So if we zoom in a little, just to show you a slightly better version of this graph. Oh, I zoomed too far. So let's change my x to like a 5, and that should make my point. Cool. So there's my shape. Sure enough, it is symmetric about the line where theta is 0, or the positive x-axis, right? So if I wanted to graph this by hand, I could actually only pick the first half of the values, and that should make the graph for me. And then I can just copy my work, right? So I could only pick the first half and then copy my work. If you wanted to graph this by hand, you could. There is a nice combination. If you want to graph something well, but you don't want to absolutely wreck yourself doing it by hand, and you have a calculator, you could sketch the graph in a calculator like this, and then you could just verify by plugging in the really easy unit circle points to make sure that your points make sense. For any of the trig functions, the easiest points are the quote-unquote corners. I realize it's a circle, so it doesn't have corners, but the axes, right? So theta is 0, pi over 2, pi, and 3 pi over 2, and then back to 2 pi. Those are the easy ones. The next easy ones would be, if you're looking at a cosine, the pi over 3s are easy because all the pi over 3s gives you a half. So if I were you, you could easily plug in just those values, and you could put that knowledge plus this together to graph a pretty good graph by hand. You don't have to graph it by hand per se, but if you were doing that, right, what I would probably do is I'd pick the easy thetas for cosine, which are theta, and then in quadrant 1, the easy one is pi over 3, and then a pi over 2 to end the first quadrant, right, and then a 2 pi over 3 and a pi, right, and then a 4 pi over 3 and a 3 pi over 2. But I'm actually going to argue you don't need the last couple, and the 5 pi over 3 and the 2 pi. And I'm going to argue that the reason you don't need the last ones is because we just tested for symmetry for a reason, right? So if you wanted to combine your calculator knowledge and do a better graph by hand than just by kind of sketching a crappy graph, you could plug in, this is going to be a -1 plus a 3, so that's a 2, right? This is going to be a -1 plus a 3 halves, so that's a 0.5 or a 1/2, right? This is going to be a -1 plus a 0. This is going to be a -1 minus a 3 halves, right? So that'll be a -2.5, right? This will be a -1 minus 3, so -4. And then what should happen is I should eventually start getting some stuff that loops around, but we'll see. So when I do 4 pi over 3, I should get -2.5, and then I should get -1. And sure enough, you see how this is the same, like they're going to start looping around. We're going to get redundant answers. When I do 5 pi over 3, I'm going to get a 0.5, and when I do 2 pi, I'm going to be back to getting a 2. So now if we were to graph this, right, notice the biggest number I have is a -4. Again, I get that that's not the most fun thing in the whole world on polar. So when you're graphing 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, you kind of make these little like concentric circles through the grid marks that you put on your axes, right? Again, totally gonna make the plug for polar graph paper because drawing polar graph paper by yourself sucks. So the only points I put on mine were the pi over 3s anyway, so I'm only gonna put those lines here. Okay, so if I were to graph this, just to show you what would happen if we graph it by hand, right? So at an angle of 0, which is here, I would move out to 2, right? And then at pi over 3, I'm at 0.5, right? And then at pi over 2, I'm at -1, which is actually going to mean go backwards down to 3 pi over 2, right? At 2 pi over 3, which is this guy right here, I'm at -2.5, so 1, 2.5, right? And then at pi, right, I'm at -4, which is going to be here. So that actually gave me half of the graph, right? Like it gave me essentially this loopy half of the graph. So the other half is going to look just like that. And you can see that if I go to 4 pi over 3 and I go to a -2.5, right, so 1, 2.5, and I go to 3 pi over 2 and go -1, right, 5 pi over 3 and a 0.5 would be here. I did a bad job of drawing it, but you get the gist. It would be that same spot. And 2 pi would be back to 2. So what you see is we get the second half of this graph. So you see how I ended up like getting symmetric pieces. And again, I draw terribly, so you get the idea. But I could have just taken the information I had when I did the blue graph and reflected the blue graph over that axis, right? Over this axis that we're saying we are symmetric about. If I reflected the blue over, I would have gotten the red stuff and it would be the same graph. So really, I could have just done up to here and then reflect across the polar axis. Now, again, I'm not going to make you graph in polar by hand literally at all. In some homework, I will ask you to give it your best attempt, but I'm not grading your skill on graphing. I think that realistically, in the world you live in now, graphing polar by hand is not a thing that you are going to be asked to do. You might be asked to analyze polar graphs, you might be asked to do things from the polar graph, but in a world of computers and graphing calculators, it does not seem like this is a skill that you're absolutely going to have to be awesome at, and that's okay. We should invest our efforts in things that seem a little bit more important.